Solving rational inequalities. In this first example, we have the following is the graph of f of x. Part A, solve where is f of x less than or equal to 0. Part B, solve where f of x is greater than 0. So first I'm going to come over here to the graph and label a couple of important things. So we have that at x equals -2, there is a vertical asymptote. So my graph is approaching the line x equals -2 from both sides. And we also have another vertical asymptote over here at x equals 3. So I'm just going to go ahead and make those dotted vertical lines or dashed vertical lines. And there's also a horizontal asymptote along the x-axis. I'm not going to go ahead and label that. What I am going to label is the x-intercepts. So I do cross my horizontal asymptote, which is fine. I cross the x-axis. I have an x-intercept at 0, and then I have another x-intercept at +4. So when I'm being asked to solve where is f of x less than or equal to 0, from a graph, what I'm really looking for is where is f of x below or on the x-axis. So I'm going to go ahead and highlight those portions. Well, I just found that I was on the x-axis at 0, and then I'm below the x-axis to the right of 0, but then there's that vertical asymptote at 3. And then if I keep moving from left to right, I see that I'm on the x-axis at 4, and then I am below the x-axis beyond 4. Now in interval notation, I'm going to describe the x values where the y values are on or below the x-axis. So the x value starts at 0 and includes 0 because that's where I'm on the x-axis. So I'm going to say x values in the interval close bracket 0 all the way up until 3, not including 3, so I have to skip over this vertical asymptote. And then if I keep moving, I saw that I was on the x-axis at 4, and then I'm below the x-axis beyond 4. So I'm going to go ahead and say my next interval starts at 4, including 4, so close bracket 4, all the way to +infinity. Now for part B, I'm interested in where is f of x greater than 0, or where is f of x now just above the x-axis? So strictly above, not on the x-axis. So this time I'm going to go ahead and highlight only the places where I'm above the x-axis. So that's going to be this part to the left of the vertical asymptote -2, and then we have another part to the right of -2, and then all the way up to 0, but I don't want to include 0, I'm above the x-axis. And then on the right side of my vertical asymptote at 3, I am above the x-axis all the way until 4, but not including 4. So if we go ahead and describe those intervals on which f of x is above the x-axis, that's going to be from left to right. I go -infinity to -2, open, so I have to jump over the vertical asymptote. And then we have -2 to 0, open. I don't want to include 0. I want to know where I'm above the x-axis. And then the next part starts at 3, so union, open parentheses 3, all the way till 4. And again, open parentheses because I want to know where I'm strictly above the x-axis. So at any vertical asymptote location, there are no y values there, so I can't include those in terms of my x values. There's no corresponding y value, then I can't say that at that x value, my y value is above the x-axis. So I have to use those open parentheses around any x value where there is a vertical asymptote. Now here in part C, we're going to use the same graph, and what we're going to do is find a rational equation, f of x, that might have the given graph. So a little bit of a review question here. So we're going to go ahead and recognize that a rational function would need my numerator and denominator. So my function f of x, I'm going to start by putting a fraction bar. And the place to start is to identify your vertical asymptotes and your x-intercepts. So we said our vertical asymptote was at x equals -2 and at x equals +3. Those are my vertical asymptotes. Now, if I have a vertical asymptote at x equals -2, those are places where the denominator is equal to 0. So that means that from knowing this vertical asymptote, I know there would be a factor in the denominator of x plus 2, because I would have to set x plus 2 equal to 0 to get x equals -2. And then the question is, well, is this factor only going to be repeated once and have a multiplicity of 1 or have a multiplicity of 2? And that depends on the behavior near the asymptote. So since near x equals -2, both the left side and the right side of the graph are heading up towards the same infinity, that means that I have a multiplicity of 2. So we have x plus 2 squared, and then from the second vertical asymptote, x equals 3, I know there must be a factor on the bottom, so factor meaning multiplied, so there's another factor, and that factor has to be x minus 3, because the only way to get x equals +3 is to set x minus 3 equal to 0, add the 3 to the other side. And looking at that vertical asymptote, the behavior near the asymptote, so on the left side of x equals 3, I have that my function is going down towards -infinity, but on the right side of x equals 3, my function is going up towards +infinity. So I have this opposite behavior here near this asymptote. So that means that the factor that it came from must have a multiplicity of 1, or really an odd multiplicity, and then if they point the same direction, an even multiplicity, but we're going to go with the least possible odd and even numbers here. So far we've satisfied the vertical asymptotes. Now the next thing would be to check the x-intercepts. So we had an x-intercept at 0, 0, and then we had another x-intercept at 4, 0. Now x-intercepts arise from setting the y value equal to 0, which is really setting, in this case, the numerator equal to 0. So that means that in order to get out an x-intercept of 0, that means in the numerator I'd have to have the factor x minus 0, or just x. And then again, it's a matter of thinking about, is this a repeated factor? So what is the multiplicity? Well, we know from graphing polynomials, higher degree polynomials, that if I cut through the x-axis like I'm doing here at x equals 0, then the multiplicity has to be 1. And then my second x-intercept at 4, 0, well, in order to get out 4, I'd have to have a factor of x minus 4. And here I'm also cutting through the x-axis, so that would have a multiplicity of 1 as well. So after you've identified your x-intercepts and your vertical asymptotes, we want to verify that the y-intercept and the horizontal asymptote are satisfied. So this function right here, I'm going to simplify it a little bit, make it look a little nicer, x times x minus 4, and then on the bottom I have that x plus 2 squared times the quantity x minus 3. So we want to just check, does this satisfy what I can clearly see is the y-intercept? So the y-intercept is 0, 0. Well, if I plug in 0, then I'm going to get 0 on the top, and I'm not going to get 0 on the bottom. I'm going to get 2 squared times -3. So I am going to get out the y-intercept. So the y-intercept is verified. So the y-intercept of 0, 0 is verified. And then I can also see from my graph that the horizontal asymptote is y equals 0, or the x-axis. So I also want to verify that is satisfied. So y equals 0. Well, to have a horizontal asymptote of y equals 0, the degree of the numerator would have to be less than the degree of the denominator. So here, if I were to multiply this out, I'd get x squared and then minus 4x. And then in the denominator, I'm not actually going to multiply it all out, but I can see I would get x squared times an extra x here, I'd get x cubed with some terms. So basically I would get a degree on the top that's smaller than the degree on the bottom. So my horizontal asymptote is verified. The last thing I'm going to do to be really thorough that this is the right answer is I'm going to plug in a test point. So I'm going to plug in a value like x equals 1 to this function that I've created and make sure that I get out a negative answer. I can see I'm going to get out some negative value. So if I plug in 1, so f of 1, I'm going to get 1 times 1 minus 4, that's negative 3. And then 1 plus 2 is 3, 3 squared is 9. And 1 minus 3, that's going to give me a negative 2. So what I have is a negative 3 over negative 18, or a 1/6. So looking here, I can see that I should have got out a negative value if my function truly represented this graph. But what happened was I got out a positive value. So what that means is that I have to go ahead and multiply by a negative with my function up here. So I'm going to have negative x and then times the quantity x minus 4 over the quantity x plus 2 squared times the quantity x minus 3. And this happened on this particular problem because our y-intercept was 0, 0. If we had had a positive or a negative y-intercept, we would have been able to tell upon working through that double check whether or not we should have multiplied by a negative at that point, but instead we found out by choosing a test point. So here, this would be our function that might have the given graph. So you can leave it in factored form. You don't have to go ahead and distribute. In this next example, we're going to solve a rational inequality algebraically. So we have the quantity x minus 2 squared over x squared plus 3x. And the first thing that we're going to want to go ahead and do is make sure the numerator and denominator are both factored completely. So the numerator is x minus 2 squared. The denominator, I'm going to factor out an x, and I'm left with the quantity x plus 3. So I want to know, where is that less than 0? Now, by being asked to do this algebraically, that means that what I want to do is go ahead and create a sign chart. That's how I'm going to go ahead and solve an inequality algebraically. So what we can't do is multiply both sides by the denominator and completely ignore it. So what we have to do is we have to find the x-intercepts and the vertical asymptotes. So those are going to be our places where our function can potentially change signs from positive to negative. So we need to find our x-intercepts and then our vertical asymptotes. Now, our x-intercepts are found by setting the numerator equal to 0. Well, that's setting x minus 2 equal to 0, so I get just x equals 2. And then vertical asymptotes are found by setting the denominator equal to 0. So I'm going to get x equals 0, x plus 3 equals 0, so x is equal to 0 and negative 3. Now we're going to go ahead and create our sign chart where we go ahead and draw a number line that extends from negative infinity to infinity. And we're going to go ahead and label these key values. So we're going to label the x-intercept at positive 2 and the vertical asymptotes at 0 and negative 3. So I want to make sure and put these in order. So I'm going to have negative 3, then I'm going to have 0, and I'm going to have positive 2. But different things happen at these values. So what I like to do is above 2, that's an x-intercept or a 0. So I'm going to go ahead and put a little z above it. And then at negative 3 and 0, I had vertical asymptotes. So you can put a little VA for vertical asymptote, but what I like to do is kind of draw a little vertical asymptote along those lines to kind of remind myself that's what's happening there on the graph. Then we go ahead and choose test points. So like we solved the other types of inequalities, quadratics and higher degree polynomials, now we pick some test point values. So between negative infinity and negative 3, I'll pick negative 4. Between negative 3 and 0, I'll pick negative 1. Between 0 and 2, I'll pick 1. And between 2 and infinity, I'll pick 3. And then we plug these test points into the most factored version of our function. So we're going to go ahead and substitute these into my x minus 2 squared over x times the quantity x plus 3. Now we look for shortcuts when we can, and here the numerator, it doesn't matter what x value I plug in, I'm going to square it. So the numerator will always be positive. So I'm going to have the numerator of all of these will be a positive number. So we're really just checking the denominator. So if I plug in negative 4 into x, I'm going to have a negative. Negative 4 plus 3, I'm going to have another negative. So the bottom, a negative times a negative is a positive. Overall, this interval is a positive interval, positive over a positive. If I plug in negative 1, I'll have a negative, and then negative 1 plus 3, that's a positive. So I end up with a positive over a negative. Overall, that is negative. And if I plug in 1, I'm going to get a positive and a positive. 1 times 4, so I'm going to get a positive and a positive. That is a positive overall. And if I plug in 3, I still have positive. So positive 3 and positive 6. So overall positive. Now we have to think about, well, what did we want? We wanted to know where this function is less than 0. So that means I want negative intervals only. So I'm going to go ahead and cross off all of these positive intervals. I don't want these, right? And I don't want where I equal 0. I want strictly when I'm less than 0. So that's going to fall within this interval from negative 3 to 0. And these dashed lines are here to remind us, well, those would have been vertical asymptote locations. I can't include those values. So it's just going to be open parentheses around negative 3 and in this example, we want to solve 3x squared minus 3x all over x squared plus 6x plus 9. When is that greater than or equal to 0? Algebraically. And then we're going to confirm our answer graphically. So again, the first step is that we do want to factor the numerator and denominator. So on the top, we're going to factor out a 3x. We have 3x times the quantity x minus 1. On the bottom, x squared plus 6x plus 9, that factors to x plus 3 times x plus 3. And we're going to go ahead and write that as x plus 3 squared. So we have 3x times x minus 1 on the top. On the bottom, we have x plus 3 quantity squared. So I want to know, when is that greater than or equal to 0? So again here, we cannot multiply both sides by the denominator. I have to figure out where are the x-intercepts or the zeros, the real zeros, and where are the vertical asymptotes. So to find the x-intercepts, I'm going to set the top equal to 0, 3x equals 0, so I get x equals 0. X minus 1 equal to 0, so I get x equals 1. To find my vertical asymptote, the bottom gets set equal to 0. So that's setting x plus 3 equals 0, or x equals negative 3. Then I go ahead and construct my number line. So from negative infinity to infinity. And I'm going to go ahead and mark these key values. So negative 3, which was a vertical asymptote, 0, which is a 0 or x-intercept, and then 1, which is also a 0 or x-intercept. Let's pick some test points. So we'll pick negative 4, negative 1, we'll have to pick a half, and then 2. And we're substituting this into the most factored version of our function. So we're substituting it into 3x times the quantity x minus 1 over x plus 3 squared. So it doesn't matter what we plug into the denominator, that's always going to be positive because we're squaring it. So the bottom is always positive. So we're really just plugging these test points into the numerator. So into this first x, I'll have a negative. Negative 4 minus 1 is another negative. So negative times a negative, that's going to give me a positive interval. And then negative 1, I'll get another negative times a negative. So overall, a positive interval. If I plug in a half, 3x would be positive, 1 half minus 1 would be negative, so positive times a negative would give me a negative. And if I plug in 2, I'll get a positive times a positive. So my final interval is a positive interval. Now we wanted to know, where is this function greater than or equal to 0? Where am I greater than or equal to 0? So I want to go ahead and cross off the interval where I'm negative, and also make sure to include, though, these places where I'm equal to 0. So we don't want to forget those values. So let's go ahead and write up our interval notation. So we're going to have x values must be between negative infinity and negative 3, not including negative 3 because there's a vertical asymptote there. We have to skip over that. And then we'll go from negative 3 to 0, including 0. And then we're going to go from 1 to infinity, including 1. So here we have our solution to our inequality. And I'm just going to go ahead and grab it and move it over to the side. And we're going to verify our answer and review sketching the graph of a rational function. So I'm going to go ahead and delete the sign chart. So now here we have an xy plane, and we already have some of the key information we need to graph. We have the x-intercepts and the vertical asymptote. So we're going to go ahead and want the y-intercept, which we actually already have, because if the x-intercept is 0, then the y-intercept is 0, 0. So we're missing the horizontal asymptote, and the horizontal asymptote is determined by looking at the degree of the numerator and the degree of the denominator, and noticing in this case that they're the same. So we're going to take the leading coefficient over the leading coefficient. My horizontal asymptote is y equals positive 3. And then because we have a non-zero horizontal asymptote, we want to see if we ever intersect the horizontal asymptote. So we set our function equal to the horizontal asymptote, 3x squared minus 3x over x squared plus 6x plus 9. Does this equal 3? So if I multiply by x squared plus 6x plus 9, we get 3x squared minus 3x equals 3x squared plus 18x plus 27. The 3x's cancel. I end up with negative 21x equals 27. And then dividing both sides by negative 21 and reducing, I get negative 9/7. So it turns out that my horizontal asymptote does intersect my function at x equals 9/7. So then we go ahead and we plot everything. So our vertical asymptote over here at negative 3, our x-intercept of 0, and our x-intercept of 1. And let's see, our horizontal asymptote of y equals 3. And we know that we're going to intersect the horizontal asymptote at negative 9/7. So let's say this is about negative 9/7. We know we're going to intersect that horizontal asymptote there at negative 9/7 and then up at 3. All right, and then now we have to just start kind of piecing together our graph. So we do know that the x-intercepts, 0 and 1, came from factors of multiplicity 1. So 1 and 1. So that means that I'm going to have to cut through each of these x-intercepts. So I'm going to put like a little C there to remind myself I'm going to have to cut through those. And then the vertical asymptote came from x plus 3 squared. So since that multiplicity is 2, I know that the behavior near the vertical asymptote is going to have to head towards the same infinity. So I'm going to go ahead and start where I kind of have the most amount of points. So I know I intersect at negative 9/7, and I'm going to go ahead and go from that point and cut through 0. And I know that I'm going to have to cut through at 1. So I have to turn around, and then I'm going to keep going, and I have to approach the asymptotes at the ends of the function. So I'm going to have to approach this direction. And then here, I know I can't go back down because then I'd create another x-intercept, which I do not have. So this is just going to have to keep on going up towards the asymptote. All right, again, I have to approach the asymptotes. And then I'm going to need to fill in the part on this side of the graph. The graph has to exist everywhere except this vertical asymptote location. So since the multiplicity was 2, if the right side of the asymptote is pointing up, then on the left side of the asymptote, I also have to point up. And then I have to approach the horizontal asymptote. And I know I don't cross it because I only had one location where I crossed it. So this is my graph of my function. And if we wanted to verify where is this function above or on the x-axis, I'm going to continue with my highlighting here. I'm above the x-axis from -infinity to -3, from -3 to 0, and that's where I'm on the x-axis, and then on or above the x-axis from 1 onwards. Right? So it takes more effort to graph it in order to solve the inequality than it does to just create a sign chart, because we only needed the x-intercepts and the vertical asymptotes to create a sign chart. But to get a good enough graph, we did need some more information. So creating the sign chart on a more complicated function is going to be less work than graphing the function to read the graph for when am I above or below